So, coming to the end of infinite series, and let's start with this general idea. The book goes into a long narrative. I'm going to sort of adapt it and shrink it down for our purposes. There are many different ways that the equal sign gets used. When we say let u equal x squared, for example, we're using it as an assignment. We use equal signs to identify identities, things that are true for all values x. We use equal signs to say that these two expressions are arithmetically equivalent. In the case of the power series, what we are saying is that this particular expression is totally equivalent to the infinite series on the other side. But we also know that that's only true inside the interval of convergence. That the identity is only true with a particular range of values of x. Now you could say to yourself, I remember doing this problem. I think we started by doing something like taking u, negative u squared, and so we do that sort of substitution. Every place we see the x in the power series represented by the geometric series. Sorry, the power series representation of this expression, and we end up with this particular power series. But for what values of x is that really true? Is it true for all values of x? Or is it only true for the values of x that made that geometric series converge? And in this case, we say only if x is in the interval from -1 to 1 is that identity true. We call that interval from -1 to 1 the interval of convergence. We say that this power series has a center. By inspection, can we see what the center of that power series is? 0. And that's because power series tend to look something like this. Power series with centers at 0 tend to have this look about them. While power series that have centers someplace else, this would be an A. Tend to have that look about it. And then you looked at it and said, oh, it looks like we're the top 4, centered at 0. I want you to look at the interval of convergence, and I want you to say, where is the very middle of that interval? What's the middle number between -1 and 1? It's 0. Is that a coincidence? No, it's not. Last question. If I had to measure from the center of something to the edge of something, what might I call it? A radius. And then by inspection, if we have this particular interval of convergence centered at 0, what might the radius of that particular interval be? 1. The distance from the center, 0, to either edge is 1. We say that the radius of convergence for this particular problem is 1. And we signify it by the letter R. In fact, today's lesson was taught by the letter R. And the number's 5. Actually, no. Actually, they always it's brought to you by 2 letters and 1 number. Okay, we're on track. Back on track. So, how does this show up graphically? Here's the graph of the function 1 over 1 plus x squared. It's defined everywhere. There's no place where that function isn't defined. But as the point I'm trying to make, the Taylor polynomials only mimic that function on the range from -1 to 1. You can see how similar it is in this area, and then how it diverges away from the interval from -1 to 1, outside our interval of convergence. Now, things that we're going to talk about today. Now, we've already introduced the idea of a radius of convergence. Now the question is, can we develop a methodology to find those intervals of convergences and their radiuses of convergences, radii of convergences, radii of convergence, and in general, do a better job of looking at series and try to figure out whether they're convergent or divergent. So, on with theorem number 5. I'm sorry? So let's start. Let's get this idea down and let's talk about it. Okay? It says, if we start with the power series, meaning a sub 0 plus a sub 1 times x, a sub 2 plus a sub 2 times x squared, and then it's centered at 0, or the alternate form is not centered at 0. If we start with a power series, there are 3 possibilities for that power series and how it converges. Possibility number 1 is that there is a radius of convergence that radiates from the center of the power series. Now, they use the expression that absolute value of x minus a is greater than r. This is true for the absolute value of x minus a is greater than r. So that's the divergence. I want the interval converges. That it converges when it's less than r. I don't like that form. I would prefer that you look at it in this form. Can we rewrite this absolute value stuff? I think I take this r and make it negative, and I put x minus a in the middle, and then I say less than r on the other side. By the way, we always talk about radius of convergence. The radius of convergence is being a positive number. And then if I solve for x by adding a to all 3 areas, essentially I say that the the interval of convergence is any value x that is between a minus r and a plus r. I like that form better. If you start at the center, and if you go down 1 distance r, you get the lower bound. If you start at the center, and you go 1 r up, you get the upper bound. So one possibility for a power series is that there's a radius convergence r, and the interval of convergence goes from a minus r to a plus r. But there are also 2 other possibilities. Second possibility is that the series converges for every value x. And we saw examples of that in the last lecture. E to the x has a power series that converges everywhere. Sine and cosine have power series that converge everywhere. Lastly, there could be a 0 radius for convergence. In the 0 radius situation, the only place the power series will converge is at the center. We are guaranteed that any power series converges at its center because of the nature of what the power series is. I'll do the one centered at 0. Okay, so there's our power series centered at 0. What happens if we put the center number into all the terms x? Well, if we put zeros in wherever there's an x, all these terms go away. What's left? Just a naught. So we say the power series has at least one place where it's going to converge at its center. Otherwise, you're either going to have a radius of convergence with an interval, or it's going to be converging everywhere. So, there's our introduction to radius of convergence. Now it's time to do some practice. Ready? Oh, you're not ready, but I'm going anyway. We touched on this topic way back in 9.1. Let's hit it one more time. Again, the last thrust of what we're doing in this chapter is, hey, given some series, are we convergent or divergent? The easiest thing that we can test for is divergence, and the way we test it is called the nth-term test for divergence. If we have a series, and if the nth term is either, if the limit of the nth term doesn't exist, or the limit of the nth term is anything other than 0, that series is divergent. Here's example number 1. Would you give me the first 3 terms of that series? One plus 1 plus 1. Okay, great. What's the nth term of that series? 1. What is the limit as n approaches infinity of that nth term of 1? 1. Okay. That limit does not equal 0. My conclusion is the series from which it came is divergent. Example number 2. Give me the first three numbers in this series. 1, 2, 3. What is the nth term in this series? N. So what is the limit of n as n approaches infinity? Does not exist. It's that special case of does not exist that it goes to infinity. In either case, what's our conclusion about the original series from which that term came? Just like the other one, it's divergent. Okay. And last example. Negative 1 plus 1 minus 1 plus 1 minus 1 plus 1. That series is popping back and forth. What do we know about the limit as n approaches infinity of negative 1 to the n? Actually not equal to dne. And our conclusion therefore is that series also diverges. Okay? Oh, this is the nth term. That always is the nth term. Now, the problem is people want to take this rule too far. It says if it's not 0, if the limit doesn't exist, it's divergent. It doesn't say anything about convergence here. The limit equaling 0 is not sufficient evidence for convergence. Okay, I think that works. And then say, nth term test is only good for showing divergence. You may not use this as a test for convergence. Guy goes into a doctor's office. He complains that his arm hurts. Do an x-ray. X-ray is good at confirming that the arm is broken. It's not good for confirming that it's carpal tunnel, or that's cancer, or it's some other malady that would cause his arm to hurt. The test is good for showing divergence. Don't make it do something it can't do. All right. Let's go and look at some other tests that will work for showing convergence. First one that we want to talk about is the direct comparison test. First of all, please note the restriction. This only works if the terms of the series are non-negative. Maybe 0, can't be negative. Item B. A sub n, the series that we're trying to prove something about, converges if it compares against a known convergent series, let's call it C sub n. As long as A sub n is less than C sub n for some n greater than big N. Now, again, that's a lot of mathematical mishmash. Let me try to describe physically what we're talking about. This is sort of like a sandwich theorem. It's sort of like half of a sandwich theorem. Right? Ryan, you're going to put out your hand. And your hand, right there, your hand is one value in the series A sub n. My hand, hovering over Ryan's hand, this is one term from the series C sub n. And here we are at some value n, and my hand's above his hand. Maybe his is adding up a quarter, mine, I'm adding up a third. Who knows? As we go on in the series, his hand always stays below my hand, and my hand represents a series that if you add up all the terms, will converge. Every time I add a value, he adds a value, but his value is smaller. My sum is finite. It eventually goes down to 0. His sum is finite. It also eventually goes down to 0. But mine is always a little bit bigger than his. What may we conclude about his sum? It's going to be convergent, meaning his sum is finite as well. They chose the expression C sub n because his sum converges. He's always below me. I am converging, so is he. Now we compare and contrast that to the item B, where we have another series, A sub n. Anthony, would you provide the A sub n series, please? And I've got this other series, I'm going to call it D sub n. And it's always below Anthony. Mine is a known divergent series. And his series is always at or above mine. My series has an infinite sum. What about his? Because you're always bigger than me, and I'm already infinite. You're bigger than infinite. So, in order to do the direct comparison test, one, we have to have a feeling of what to compare it to. And it also has to be, if you're comparing it to something that's convergent, the thing that you compare it to always has to be smaller, so that I can prove that compares and goes and is convergent. Or if I'm comparing it to something that's divergent, the other one's got to be bigger. So let's take a look at this example. The series from n equals 0 to infinity of x to the 2n over 2 factorial squared. Did I mention you have to know another series to compare it to? And since we're going to prove that it converges, whatever series I produce better be bigger than this. So let's go through some known series. Now this has got an n factorial in the bottom. Kind of reminds me of e. Kind of reminds me of the series for e to the x. E to the x is equal to, not equal to, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. You haven't memorized that yet. I could just do it sooner. The nth term is x to the nth over n factorial. How does that compare to what we have? Square in the bottom, so it's going to be smaller than that. But what about comparing x to the 2n there, but I'd like, again, only an n there? You know what? I can make these a little bit closer. Jessica? What if I compared it to, how about this series? Oh, not that series. The thing so. There, that's the series I want. Can I do that? Can I simply look at that new expression, e to the x squared, and write out its power series? I think I can go and substitute every occurrence of the value variable x in the original one with x squared, and I can get that. This would be x squared, which is x to the 4th. This would be x squared to the 3rd. X to the 6th. I think I get x squared to the nth over n factorial. Is that almost equivalent to what we had there? I got x squared to the n, which by the way is just another way of saying x to the 2n. Everything's the same about these two series except for the n factorial. Wait, do I know if this series converges? I think it does. I think I did a substitution. No, since I did a substitution on a series that was convergent everywhere, that the new series also converges everywhere. Yep, that's the rule. Check mark. So the series that's representing e to the x squared, it's a known convergent series. This other one is nearly identical, but alas, its denominator is bigger, which makes each term smaller, which means this one converges, e to the x squared. Here's this one, it's smaller. This one converges. What do we know about the one that's below it? Run into the ground. It also converges. That's what I mean by using a known convergent series to compare. All right. Let's try something else. Another definition. Definition for absolute convergence. In the previous example, we had a condition that all the terms, to do the comparison test, all the terms have to be non-negative. Unfortunately, some series that we have negative terms. Sometimes, in order to use that limit comparison test, we may change all the terms into what's called, or create what's called the absolute series. A series in which, instead of looking at all the values, the individual values, we look at their absolute values. If after switching all the negative signs to plus signs, we find that this series converges. We give it a new title. We call it an absolutely convergent series. We say that it converges absolutely. It's an absolutely convergent series. Now I will draw a picture. Here's my picture. What that is? I asked her that. All right. That is a circle which represents the set of all power series. Here, on this side of the line, is the set of all divergent series. On the other side of the line is the set of all convergent series. And you're either one or the other. Yep, you should draw this. And in here, are the series that are absolutely convergent. That converge absolutely. No. No. Solo. So when we say a set, when we say a series converges absolutely, it makes it a special kind of convergent series. The reason why it's special, if I'm going to add up a string of numbers and I hope that it becomes a finite sum, would it be helpful that if some of the numbers along the way were negative, instead of pushing the sum up higher and higher and higher, sometimes we get a negative number, it draws it back down? It's easier for a series to converge if there are some negative numbers in there. So, some series converge because they have these negative numbers. Some of these series that converge when they have negative numbers, once you strip them out, strip the negative numbers out, if you make everything positive, they no longer converge. But there are some very special series that even when you take the negative parts out, they still end up converging. Those are the absolute convergent series. And because of that Venn diagram, we have theorem A. Absolute convergence implies convergence. I would hope so. It seems self-evident. Like NBA All-Stars implies that they're playing the NBA. Snowy and rainy days imply that it's snowing. Absolute convergence implies convergence. Or lastly, if I'm a member of the set down here, I must also be in the member of the set called convergence. All right. So, that leads us to a question. And that is, hey, can we show that the series sine x to the nth over n factorial converges? I would really like to use that direct comparison test. Oh, darn it. Dash it all. That direct comparison test only works if all the terms are positive. Foils. Oh, can we do that? Can we just make them all these terms positive, even though sine to the nth power may be negative?
Yeah.
Sure. So let's investigate really quickly absolute value of sine to the nth power over n factorial. In order to use the limit comparison test, let's pretend the negative part don't exist.
Don't exist.
Dorothy Ashton would say, oh, Mr. Prater grew up in Taylor. He's using local color to be authentic. I grew up in a town that had a very, very high, well, I'll say it nicely, Appalachian population. I can say it nastily. Hillbillies. Rednecks.
Did you call it Taylor Tucky last year?
Everyone calls it Taylor Tucky. It is to Wayne County as Hazel Park is to Oakland County. No. So anyway, so I've got this series, the absolute value of sine x to the nth power. You know what? I think that the absolute value of sine x to the nth power over n factorial, I think it is less than 1 over n factorial. Sorry, less than or equal to, I should say. I would think that when I get the absolute value, I get all non-negative numbers. The biggest that sine x can possibly be is 1. I say it's always less than 1 over n factorial. You know what? I know something about this thing. I know it's convergent, and I know what it converges to. You know what it converges to? Nope. Any other guesses? Something between 1 and 2. Nope. Considering that this is 1 and this is also 1, I think something maybe between 2 and 3. I'm sorry, nope. Let me rewrite this. This is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, dot, 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 when x is 1. Any other guesses? 2.7
Yeah.
9 2 8. It's like I hear mumbling, and I hear you were. My very first calculus class, I got in an argument about the pronunciation of oil. And one of the students said, if E-U-L-E-R is spelled Euler, does that make E-U-C-L-I-D pronounced Euclid? Euclid. Euclid is the person who wrote the fundamentals of geometry. You studied, in high school, you studied Euclidean geometry, the geometry of Euclid. Well, this is e to the x, but if I make all of them equal to 1, which like I did here, this is exactly e to the first. So, let's see if I can summarize. Because this term, as an nth term, creates a series which not only converges, it converges to e. Because this term is always less than 1 over n factorial, the series that it comes from must also converge. But that is an absolute version of this series. My conclusion is that this series absolutely converges. And if the series absolutely converges, then it also converges. Boy, that's a lot of steps. I mean, I feel like that scene from Monty Python and the Holy Grail. Well, the one where he says, so if she weighs as much as a duck, then she's made of wood. And therefore, she's a witch. I mean, I feel like that we're making huge jumps here, but it's all, I think.
Have you seen the social network?
I have not.
It's hilarious. Oh yeah, for the other guy, it's like, so that'll be 15,000 plus the 1,000 you so that'll be 16,000. Oh,
Wait.
hold on. Okay, just checking.
Yes, you're right.
All right. So there's a lot of jumps there. I had to find a series that was known to be convergent, that was bigger than the one that I did, but I only could do that because I took the absolute value. A lot of steps. All right. How about a different test? A little one that's a little easier. So let the series A sub n be made up of positive terms. In other words, you can feel free to strip out the negatives and look at the absolute version of this if you need to. We take the ratio of the n plus 1 term to the nth term. And we take that ratio and we take the limit as n approaches infinity. And we get a number, L. If L is bigger than 1, if L is less than 1, the series converges. In other words, the n plus 1 term got sizably smaller than the nth term. And because of that, L was less than 1, and therefore the series converges. If L is greater than 1, that means the n plus 1 term was actually getting sizably larger than the nth term. The series got bigger as it went on. And that means the series would be divergent. And if L is equal to 1, this test doesn't tell us anything. Does everyone understand the ground rules? Because we're going to then probably spend the rest of the period applying the ratio test to some different situations. By the way, if I wanted to try to elicit some sort of Pavlovian response from you guys. I'm sorry? Yes. If someone says, find interval of convergence, I want you to respond, ratio test. And then have your mouth tell me. Sure, I'll say, interval of convergence.
Ratio.
Very good. Not everyone is participating in that.
I don't understand the point. What are we doing?
I want, okay, Pavlov did an experiment where if he rings the bell and then feeds dogs, after a while, just the ringing of the bell makes the dog salivate.
Right.
Okay, so what I want is you to have a guttural response to particular kinds of problems. The stimulus in this situation is the expression interval of convergence. Your response is ratio test, because the ratio test is most often used to find the interval of convergence for power series.
Why isn't it on there?
Because we don't write everything that's important on the slide. Whoops. Because Vader can't spell. Used most often in finding intervals of conversion.
Ratio test.
There we go.
What about other things we were doing before?
It's useful, but not as useful as this. This is like a gold mine. The other one's like a penny in front of the alley. Right? All right, here we go. So, wait, what? Finding intervals of convergence.
Ratio test.
Ratio test. Very good. Last year we worked on having the 18 stats class always bow their head when I mentioned Duntuki. So we all have our different classes. All have their different responses. You ready? So here is a series, and the question is, what's the radius of convergence? Radius of convergence and interval of convergence. Please put those together in your mind.
Ratio test.
Ratio test. All right. Question: what is the a sub n term for that series? And we read it right off the series. It is n times x to the n over 10 to the n. So that's one of the two things that we need to set up this problem. What is the n plus 1 term? Well, we find it by taking the nth term and changing every occurrence of n to n plus 1. So it is n plus 1 times x to the n plus 1 divided by 10 to the n plus 1. So there's our nth term and our n plus 1 term. Now it's time to write a limit. The limit as n approaches infinity of the n plus 1 term all over the nth term. My response exactly. I hate fractions. I hate fractions and side fractions, even doubly so. Yes, sir.
It'd be easier to take your A to the n formula and plug in 2 is also what it is, and then plug in 1. And then you get, like, if you put in 2 to nx, you get 2 x squared over n squared.
Okay. So I see where you're going with that. Of course, when you put real numbers in there, what happens as n approaches infinity? We get the inability to say what happens when n grows. Right? I am going to show you a way to rewrite this more easily. More easily? Is that right?
More easily as well.
Okay. Because I'm describing how I'm doing something, I have to use the adverb form. Let me get this right. The limit as n approaches infinity. Now, the thing that I do, because I hate the fractions with fractions in them, I'm going to write the top term. And instead of writing as a top, I'm going to take the bottom term and I'm going to multiply by its reciprocal. And then I'm going to go grab my black marker that I use for cancellation. Or I could use the green, use red.
Red is more of like a harsh cancel than
What? I don't think the green shows up very well on the board.
use the red.
Okay, I'll use the green, but mostly so I can tell the story about how my son was in stats class on Friday, and he yelled at me for using the black marker too much on the whiteboard, and he thought I was boring. So he gives me the green marker and says, "Daddy, use the green marker more." All right.
And he erased everything you wrote.
And I write things up and then erased it before. Okay, can we cancel? Is there any cancellations going on? How about this 10 to the n? How about this 10 to the n plus 1? Louder, Candace.
I don't know. Well, as n approaches infinity,
No. Even before n approaches infinity.
It's n minus n
Oh, you're
All of
switching
the,
to 10?
I'm getting rid of all the n's up here, the n10s up here, and getting rid of all but one of them down below. That reduces the complexity of this quite a bit. Anything else?
And x to the n.
The x to the n, and all but one of the ones up there. That's great. That means I can rewrite this whole limit as n plus 1 over n, taking this top here and taking that bottom there, times x over 10. Just rearranging the terms a little bit. Tell me more, Anthony.
Well, because n plus 1 over n is n versus infinity. And infinity plus 1 is now 30.
Okay, excellent. Could not have said that better. I'm not even going to try. I flipped them around so that you could see that that expression, that fraction, as n gets really big, is going to turn into a big whopping 1. As n gets really big, that plus 1 matters diddly squat. You essentially get an expression of n over n. So that means that this limit, after you apply the n going to infinity, is just equal to 10 over, or x over 10. Right? This expression will converge when x over 10 absolute value is less than 1. The ratio test said find the ratio, take the limit as n approaches infinity, and when the ratio is less than 1, you have a series that converges. Another way of saying that would be to say, take this result, which is equivalent to our L statement in our little write-up, and say, okay, make it less than 1. For what values of x will this expression be less than 1? Well, negative 1 is less than x over 10 is less than 1. What else can we do? Multiply everything by 10. Our ending answer is that the interval of convergence is negative 10 to 10. And I could ask you the final question, which is the one that they started with. What's the radius of convergence then? The center is at what? Center is at 0. So the radius of convergence is 10. From 0 to 10 up, from 0 to negative 10 to go down. All right. This one's a lot easier. I'm going to zoom through it. The limit as n approaches infinity. The n plus 1 term which goes on top is n plus 1 factorial times x to the n plus 1. The nth term that goes on the bottom is n factorial x to the n. Can we cancellate? Cancellate. Can we cancel anything? Zoop. Zoop. What about this? It ends up that those two cancel and leave just an n plus 1 on the top. N plus 1 factorial is n plus 1 times n factorial. The two n factorials cancel. Now as n goes to infinity, this bad boy goes to infinity. Meaning, there are no values of x that create the interval of convergence. This series is only convergent in one location. And that location is at its center, at 0. All right, I know you're packing up your bags. But indeed, you can do most of this assignment at this point. We've got a few more slides to go, but you need to start tackling it now because, again, we are under the gun. Aaron. Probably not.
Okay.
My biggest concern right now is trying to finish the material.
Did you say something about a take-home test last time?
Oh, there's a very large possibility of such a thing.
Okay.
All right.
Would that be for, sorry, would that be for 9 and 10 or just for 9?
No, this being for 9. There's enough material in 9 to.
Are we ever going to learn hyperbolic functions?
Yeah.
One second. Let me. No.